Okay, I want to solve one equation, just one. X times e to the x equals 5. Let me actually try, not hand wave, try. Attempt 1. Divide both sides by x. That gives e to the x equals 5 over x. An exponential on the left, a rational function on the right. That's worse. Two different species of function staring at each other. Attempt 2. Take the natural log of both sides. The log of a product splits apart, so I get log of x plus x equals log of 5. Wait, look at that. The logarithm didn't free x, it just moved the entanglement. Now x is trapped inside a log and also standing alone outside it. Same disease, new symptoms. And here's the thing. This isn't me being bad at algebra. It is provable that no finite combination of additions, multiplications, powers, exponentials, and logarithms will ever isolate this x. The equation lives outside the elementary functions. Genuinely, outside. So the tools don't fail because I'm using them wrong. They fail because the toolbox is missing a tool. Let me back up and ask a more honest question. What am I actually doing when I solve an equation? When I solve x squared equals 5, I apply the square root, the inverse of squaring. When I solve e to the x equals 5, I apply the natural log, the inverse of exponentiation. Every act of solving is secretly the same act. Apply the inverse function. So the real problem isn't the equation. The real problem is that nobody has handed me the inverse of the map f of w equals w times e to the w. Fine, then let's build it from scratch. And to invert a function honestly, you first have to know it intimately. Let me interrogate this function. F of w equals w times e to the w. At w equals 0, 0 times 1 is 0. So the curve passes through the origin. For w positive. Both factors are positive, both increasing. The function rockets up to infinity. That part is easy. For w negative. Now it gets interesting. W is negative, but e to the w is still positive. So the product is negative. The entire left half of this curve lives below the axis. And as w marches off to negative infinity, two forces fight. The linear factor, w, pulls the product toward negative infinity. The exponential factor, e to the w, collapses toward 0. Who wins? The exponential always wins. Exponential decay crushes linear growth. So the product goes to 0, sneaking up from below. The negative x-axis is a horizontal asymptote. Now hold on. Follow the logic. The curve comes in from the far left, hugging 0 from below. And it has to return to 0 at the origin. But in between, it is negative. So it must dip down and come back up. There has to be a lowest point, a minimum. But where? Differentiate. Use the product rule. F prime of w equals e to the w plus w times e to the w. Factor out the exponential and you get e to the w times 1 plus w. Stare at that. E to the w is never 0. So the only place the derivative vanishes, the only critical point on the entire real line, is w equals -1. And the value there? F of -1 equals -1 times e to the -1. That is -1 over e. about negative 0.368. Check the sign of the slope. To the left of negative 1, the function is falling. To the right, it is rising. So negative 1 over e isn't just a minimum. It is the global floor. There is no input anywhere that makes w times e to the w dip below negative 1 over e. Remember that number. It is about to control everything. Now here is a beautiful move. Let's solve w times e to the w equals c just by drawing a horizontal line at height c and counting how many times it hits the curve. If c is positive, or 0, the line cuts the rising right arm exactly once. One solution. If c is exactly negative 1 over e, the line just kisses the very bottom of the dip. Exactly one solution. W equals negative 1. If c is between negative 1 over e and 0, now the line slices clean through the dip and hits the curve in two places. Two solutions. One on the falling side and one on the rising side. And if c is below negative 1 over e, nothing. No intersection. The equation has no real solution at all. Two solutions inside that strip. Hold on to that fact. It is about to become the single most distinctive feature of our new function. To invert a function, you swap input and output. And geometrically that means reflect the entire curve across the diagonal line. Y equals x. And actually, here's a trick I love. You never have to solve anything to draw this. Every point on the original curve looks like t and t times e to the t. Just swap the two coordinates. Plot the point t times e to the t and then t. Let t sweep across all the real numbers, and the points you paint out are the graph of the Lambert W function. By definition, no solving required. That is literally how you can plot it in any graphing tool. So let's reflect piece by piece. That horizontal asymptote on the left becomes a vertical asymptote. As x creeps towards 0 from the negative side, one branch of our function plunges straight down to negative infinity. The minimum point, at negative 1 over e, reflects into the point, negative 1 over e, negative 1. And this becomes the sharp fold in the graph, the branch point. And here is a subtle, gorgeous detail. The original curve had a flat, horizontal tangent at its minimum. But reflection swaps horizontal and vertical, so our new function arrives at that fold with a vertical tangent. It comes in standing straight up. But now, a problem. Between x equals negative 1 over e and x equals 0, the reflected curve fails the vertical line test. Of course it does. That is exactly the strip where we counted two solutions. And a function is not allowed to give two answers. So we slice the curve into two separate functions. The first, called w0, the principal branch. It starts at the fold, climbs up through the origin, passes through the point e, 1, because 1 times e to the 1 is e, and then it grows forever, but slower and slower. For large x, it behaves like log of x minus log of x. Logarithmic growth with a logarithmic correction. The second, called w-1, the lower branch. It starts at the very same fold and dives down to negative infinity as x approaches 0. Two branches, sharing one birthplace. Now, a real function deserves a derivative, but our function has no formula, so we differentiate its definition instead. Start from w times e to the w equals x. Differentiate both sides with respect to x, remembering that w itself depends on x. The left side needs the product rule and the chain rule. You get w prime times e to the w plus w times e to the w times w prime equals 1. Factor out w prime and solve. W prime equals 1 divided by e to the w times the quantity 1 plus w. Think about what just happened. We found the derivative of a function we cannot even write down. And this little formula confesses two secrets immediately. Secret 1. At x equals 0, w is 0. So the slope is 1 over e to the 0 times 1. That is just 1. The graph leaves the origin at a perfect 45-degree angle, which makes sense. For tiny values, e to the w is nearly 1, so w times e to the w is nearly just w. Near 0, the function is almost its own inverse. Secret 2. When w equals -1, that is, at x equals -1 over e, the denominator becomes 0. The slope blows up to infinity, the vertical tangent at the fold. The calculus confirms exactly what the reflection promised us. Everything is consistent. Can we compute this thing with pencil and paper? Let's guess that w is a power series. W equals a 1x plus a 2x squared plus a 3x cubed, and so on. Substitute that back into the defining equation and match the coefficients term by term. Grind it out, and a stunning pattern appears. W of x equals x minus x squared plus 3/2 x cubed minus 8/3 x to the 4th plus 125 over 24 x to the 5th and onward. The general coefficient is n to the power n minus 1 over n factorial with an alternating sign. And how far does this series work? Run the ratio test, and the radius of convergence comes out to be exactly 1 over e. That is not a coincidence. The series converges precisely up to the distance of the branch point at -1 over e. The power series, computed blindly at the origin, can feel the fold from far away. Singularities cast shadows. And right at that fold, near its minimum, the function w times e to the w looks almost exactly like a parabola. And when you invert a parabola, you get a square root. So near the branch point, w is approximately -1 plus or minus the square root of 2 times the quantity 1 plus ex, a sideways parabola. The plus sign is the upper branch climbing out. The minus sign is the lower branch diving down. One formula, both branches, born from the plus or minus of a single square root. That is why the graph folds the way it does. Now everything falls into place. X times e to the x equals 5? The answer is w of 5, which is about 1.33. X times e to the x equals -0.2? We are inside the two-solution strip, so there are two answers, about -0.26 and about -2.54. Both are correct. What about x to the x equals 2? Take logs. That becomes x times log x equals log 2. Substitute x equals e to the u, and it turns into u times e to the u equals log 2. So u is w of log 2, and x is e to that. About 1.56. And one last one. Where does e to the -x cross the line y equals x? Multiply through by e to the x, and it becomes x times e to the x equals 1. So x equals w of 1. About 0.567. A number so fundamental, it has its own name, the omega constant. And when a computer actually plots this curve, or evaluates it, it runs Newton's method. It repeatedly improves a guess. Using the update, w becomes w minus the error divided by e to the w times 1 plus w. And look, there is our derivative again. e to the w times 1 plus w, doing the work. Just a handful of steps for every single point on the curve. That is what is happening under the hood every time this graph gets drawn. But wait, that staircase went by fast, almost too fast to believe. So let me slow it all the way down, because I don't want you to trust the machine. I want you to become one. And here's the part I love. You could do this yourself, tonight, with paper. Watch one step in full. My guess is w equals 1.13. I compute e to the 1.13, about 3.10. Multiply by w, about 3.50. But I wanted 5. So my error is negative 1.50. Now divide that error by the derivative. E to the w times 1 plus w, about 6.59. That gives roughly negative 0.23. Subtract it from my guess. New guess, 1.36. Do it again, and I get 1.327. Once more, 1.32672. 3 steps of arithmetic, and I have 6 correct digits, and every step roughly doubles the digits. This is not computer magic. This is a pencil, a derivative, and patience. So step back. Look at what we built. This function is provably non-elementary. No finite formula in powers, exponentials, and logarithms will ever equal it. So this was never a notation trick. We built a genuinely new mathematical object. It has a definition. It has a domain carved out by a horizontal line test. It has a derivative found by implicit differentiation. It has a power series whose radius of convergence secretly encodes its own singularity. And it has a graph whose every feature, the fold at negative 1 over e, the vertical tangent, the 2 branches, the slow logarithmic climb, all of it traces back to one single line of calculus. F prime of w equals e to the w times 1 plus w. One derivative, one critical point, an entire function.